guys, welcome to AMK Resource World. Your success, our motto. In this video, we are going to talk about the working principle of PN junction diode as well as we'll discuss the characteristics of PN junction diode. Okay guys, before we start talking about this PN junction semiconductor diode, we will have some discussion on semiconductor. So because we should know what is a semiconductor and types of semiconductors, so that we can start with this topic, that is PN junction semiconductor diode. Okay, so now what is a semiconductor? It is a material whose conductivity lies between conductor and insulator. So we know this, and also we know that we have two types of semiconductor materials. Which are those? So we have intrinsic semiconductor material and we have extrinsic semiconductor material. Okay, so what do you mean by intrinsic? See, intrinsic semiconductor material is a pure form of semiconductor material which has no impurities in it. So we can also call this as pure semiconductor. So the another type of semiconductor we have is extrinsic. Now, what is extrinsic? So when impurities are added to the pure semiconductor material, then it is called as extrinsic semiconductor material, which is also known as impure semiconductor material. Okay, which are the semiconductor materials? We have silicon, germanium, gallium arsenide. Yeah, these are the semiconductor materials available, using which we can build semiconductor devices and components of electronics. Okay, so here coming to extrinsic semiconductor, as we told that when we add the impurities we are going to get this extrinsic. So what type of impurities we are adding, and do we have types in extrinsic? Yeah, so we have two types of extrinsic semiconductor material, that is P type and N type. So we call them as P type semiconductor and N type semiconductor material. Okay, so when we get this P type semiconductor and when we get this N type semiconductor material, see, we have different types of impurities like trivalent impurities, pentavalent impurities. So when we combine these impurities with the pure silicon or the pure semiconductor, we are going to get either P type or N type. So to get P type, we need to add trivalent impurities with the pure silicon. To get N type, we need to add pentavalent impurities with the pure silicon. Okay, so example here, let us say boron. Example here, let us say phosphorus. See, these are the impurities which we are going to add with intrinsic, so that we can get extrinsic, that is P type. The same thing, if you add this phosphorus with intrinsic, then we'll get extrinsic, that will be of N type. So like this we get P type semiconductor material and N type semiconductor material. Okay, now let us start with PN junction diode. So first I will take P type semiconductor material, then I will take N type, then we'll join them. So let us do that. So I am taking a P type and I am joining this with the N type. This is a P type and this is an N type semiconductor material. As we know, here P type semiconductor material has majority holes and minority electrons, whereas in N type semiconductor material we have majority electrons and minority holes. So let us represent the majority charge carriers inside this P type semiconductor material using this plus symbol, and let us represent the majority charges, that is electrons, in N type using this minus symbol. So this is our structure of a PN junction, you can see that we have just joined this P with N, because of which we got a junction here, and that's why we are calling this as PN junction. And the name which is given to this PN junction, it is a diode. Okay, so we'll see here what is a diode, how it works, and what are its characteristics. So here, when we join these two structures like this, what happens at room temperature? So here I will just draw another figure to represent this more clear. So what I am doing here is just giving you the clear picture what happens at room temperature when these two junctions are joined, brought together. Okay. Okay, you can see here in this diagram, at room temperature, the majority charge carriers which are present in P, that is holes, and the majority charge carriers, that is electrons, which are present in N, they start diffusing from N region to P region, and the holes, they start diffusing from P region to N region. You can see here some of the electrons, they have diffused from N to P, and some of the holes, they have diffused from P to N, for finally leading to the formation of a depletion layer. So not only it is forming a depletion layer, it is providing a barrier potential so that no further charges can be diffused from N to P and P to N. See, this is called as our PN junction diode, right? Now let us see the working of this diode, how we can make this diode to operate. So before that, first we'll see the symbolical representation of the diode. See here, a diode can be represented with a symbol like this, and this is called as anode and this is called as cathode. This is our P region and this is our N region. So you can say this is anode, cathode, and this is P and N. So this is the symbol which is used to represent PN junction diode. So it will be easy for us to use the symbol in our circuits so that it gets simplified instead of writing this structure every time where we use this diode. Okay, so here see this diode, it can be operated, diode can be operated in two regions. See, diode can be operated in two regions, that is forward region, we also call this as forward bias. Second, reverse bias. That means we can operate a diode in two regions, that is we can forward bias the diode and we can reverse bias the diode. So what do you mean by bias? Bias is nothing but connecting a supply to the device. So if you are connecting a battery to the device, then we say that the device is biased. So now it depends on the terminals of the battery whether it is forward biased or it is reverse biased. So now let us see what happens to the diode when it is operated in forward bias or when it is operated in reverse bias. So once we go through the working of this, then we will plot the characteristics of this diode that is the VI characteristics of the diode. Let's talk about, let's see what happens to the diode when it is forward passed and how it works. So here, to forward pass this diode, I will just take a battery here with terminals plus and minus. So the positive terminal of this voltage is connected to the P region, and the negative terminal of this battery terminal, the voltage source, is connected to the N region. Let us say this is a voltage source which is connected to the diode. Now the diode is said to be forward passed because plus is connected to P, minus is connected to N. Now these charges from P, they get repelled because of this positive terminal, and the charges in N, they get repelled because of negative terminal. So they don't start diffusing from P to N until the supply voltage is greater than the barrier potential which is developed in this depletion region. Okay, so inside this depletion region we have some barrier potential. Okay, so that barrier potential is due to the internal electric field which is developed while forming that depletion region. Okay, so how much voltage I should give here so that it opposes the barrier potential in the depletion region, and then the charges can start flowing from P to N and N to P. That is nothing but the current starts flowing from P to N. Okay, so here the minimum voltage which we need to give is how much? 0.7 volts if it is a silicon diode. So if it is a silicon diode, the minimum forward voltage is 0.7 volts. That means if I give voltage here 0.7 or above 0.7, then the barrier potential which is developed across this depletion region gets opposed and the charges start flowing from P to N, leading to a forward current, that is IF. That means when the diode is forward biased, a current flows through the diode, that is forward current IF, if the voltage here is greater than or equal to 0.7 for a silicon diode. And once the diode gets turned on, so we call this condition when current starts flowing in the forward direction, when the voltage is greater than or equal to 0.7, then the diode is said to be turned on. So when diode gets turned on, there will be a voltage drop across the diode. How much? That is the voltage drop here, that is forward voltage drop, that will be equal to 0.7 volts. Okay, so these things we should remember when we are talking about the forward bias of a diode. So let us draw the forward characteristics of this diode. So I am taking x-axis and y-axis here. Let us say the x-axis is volts here, voltage in terms of volts, and y-axis is forward current IF in terms of milliamperes. So let us write this. Fine. As we discussed what happens in the diode when it is forward bias. So here when the voltage given to the diode is equal to or greater than 0.7, then the current starts flowing through the diode. We call that as forward current because the current is flowing from P region to N region. When the voltage is less than 0.7, the diode does not allow the current to flow through it. During that time, what will be the characteristics? See, when the voltage for, let us say here we have forward voltage VF, that is 0.7 volts. Fine. So until we give this 0.7, the current will be very small here. So once the voltage becomes equal to 0.7 or greater than 0.7, the diode gets forward bias and the depletion layer width decreases to allow that current, and there will be a flow of large current through the diode, and that we call that as forward current. So here you can see how the current increases when the supply voltage is equal to or greater than 0.7 when the diode is forward biased. So this is the forward characteristics, how it looks when we plot this in a graph. Okay, now let us see what happens to the diode when it is reverse biased. So for this I will take one more diagram so that we can understand this in a better way. So I am just writing the depletion layer expanded here. Okay, so we'll come to know why we are doing this. So let us say we are reverse biasing this diode. So to reverse bias, I need to just reverse the terminals of the battery. So plus should be connected to N here and minus should be connected to P region. As you can see here, the width of the depletion layer I am expanding. Why? Because we have connected the supply voltage in reverse order. So when we connect this negative for this P region and positive for N region, the charges in P, they start moving towards the negative terminal, and the charges in N, they start moving towards the positive terminal. Okay, and what happens to the depletion layer? The width of the depletion layer expands because the field which is applied now, it is along the direction of the internal field of the barrier potential. So the current does not flow at any cost from P to N. The width of the depletion layer gets expanded finally, which leads to zero current from P to N, or we can say some small negligible current which will be flowing from P to N due to minority charge carriers, and we call that current as reverse current, and we call that current as reverse current. Okay, and you can see here, let us plot this in the characteristics. So because of minority charge carriers, so we'll get some reverse current, negligible reverse current, and that will be in terms of nanoamperes, and up to certain voltage, up to certain reverse voltage. This is our VR and this is our VM. So up to certain VR, we can say this diode acts as a switch off because no current flows through P to N in the forward direction, and even though the current is flowing because of minority charge carriers, that is very small, negligible, almost equal to zero. So we call that in nanoamperes, right? So now this diode, it has a certain limit of reverse supply voltage. So we cannot give a reverse supply voltage beyond its breakdown voltage. So what is breakdown voltage? The voltage at which the P region gets converted into N region and N region gets converted to P region due to expansion of the depletion layer. So complete P gets inverted to N and N gets inverted to P, which further leads to a large flow of current in reverse direction, and the voltage at which this happens is called as reverse breakdown voltage, and we are going to show you that here in the characteristics. So let us say this is VBR, this is the voltage at which the regions get inverted and finally complete region is occupied by the depletion layer, and a large reverse current starts flowing from N to P in the reverse direction. So once we reach to that VPR, then suddenly there is a rise in current which is known as reverse current. Keep watching our videos. If you like our video, then like, subscribe and share to your friends. We will be back with more such videos. AMK Resource World, your success, our motto.